Previously, we learned how to do calculate the correlation R using the sample, and this is the second part of correlations, Pearson correlations. And okay, just like all the other statistics we've looked at, a sample correlation is subject to sampling error. So we got the R equals to 0.68 the other last time, which is pretty strong correlation, but that could be due to a sampling error. So if you take a different sample of people, for example, you might get a lot smaller correlation, and so we're gonna have to kind of know, whether it happened due to the sampling error, or we're gonna have to kind of calculate the chance of this happening by chance due to a sampling error. And so that how we can do that, that's what I'm gonna talk about here. So we're gonna do a hypothesis testing for correlations for the value of R we get. Just like z-test, t-test, and ANOVA, we can use a null hypothesis and either reject or fail to reject. So let's look at the example. So this is the same setup of family income and the grades in school. So researcher believes that family income is positively correlated with grades in the population. So that's a one-tailed test. And let's say he takes a random sample of 14 students and records their family incomes and grades, then calculates the sample-based correlation R between family income and grades. That's why we already know how to do this because we did it in the last class. And so, okay, so I'm going to skip the actual calculation. Okay, this is the sample data, and you get R equals to 0.65 from this. And scatter plot is like this. Okay, then the sample correlation of 0.65 supports his theory, but it could be a result of sampling error. There could be actually no relationship in the actual population. So the researcher must do a hypothesis test before he can conclude there is a positive correlation in the population, instead of it having happened due to a sampling error. The chance of this happening as a sampling error is if it's so small. In other words, if it falls within a critical region, then we can be sure that there was a correlation. So the US researcher hypothesized that there is a positive correlation. We do a one-tail hypothesis test. And of course, null hypothesis. Okay, this is rho. Okay, this is the alphabets for R. Correlation, and population is a parameter for correlation. So rho, if there's a positive, if the assumption is that there's positive relationship, then the null hypothesis would be no relationship or negative relationship. So no relationship is rho equals to 0, and negative relationship would be minus negative. Okay, so that's what it is. And this is the alternative hypothesis, of course, positive. Rho is going to be positive, meaning it's a positive relationship. Okay. Now, We have to determine the critical value for the Pearson correlation because, you know, this sample distributions, you know, if they falls into critical region, then we can reject our hypothesis. So we're gonna have to know a critical value of Pearson correlation. And there's a table. Just a sec. So the table is this. This is a table you can use for the hypothesis test. So you have to know degrees of freedom, and also you have to know whether it's one-tailed or two-tailed, and then also you need to decide what alpha level you're using. So in this case we are doing one-tail test, and alpha level is 0.05. And what's the degree of freedom? It's you know, the population, I mean sample size minus 2. So in our example we have 14 people, so it's going to be 12. So 12, and here it's going to be 0.458. It's a critical value. Of R is 0.458. So if the R is larger than 0.458, that means the correlation R was well, the chance of it happening by sampling error is so small, so it's got to be the actual correlation. That's how you conclude. So our correlation is above the critical value, so we reject our hypothesis. You know, not P, this is rho, you know, equals to 0 or less than 0. And we know that the P value is less than 5%. So that's how you can just say P is less than 5. So we conclude that the population correlation between family income and grades is greater than 0. We can be sure that it was not due to a sampling error. And then we can then we can stop this whole correlation thing. To summarize the conclusion, we can say something like, the analysis indicated that family income and grades were positively related. R equals to plus 0.65, N equals to 14, and P is less than 0.05, and one-tailed. Again, just as the other statistical testing. Okay, now we are sure there was a correlation, but it doesn't mean the correlation was, you know, strong enough, large enough, and important. It doesn't mean that. Practically important doesn't mean that. So, you know, it could be a very small and still be, you know, what it means, it goes two ways. You know, the correlation can be very small and still be significant. No, that's what I meant. I mean, correlation, you know, maybe small, you know, in a practical sense. In a practical sense, you know, it may not be large enough, even though statistically speaking, the correlation was significant. And this is what I don't really understand, you know. you can find the significance if you have large sample size. Why is that? I don't really understand that point yet. Anyway, so to evaluate the practical importance of a Pearson correlation, we calculate R square, and it's like effect size, but it's not exactly effect. There's no effect in correlation, so we call that coefficient of determination. Another thing to remember about coefficient of determination. That's like effect size equivalent in correlation. So R square would be 0.42, and this is a guideline. So in this case, it's a large correlation. What it means is that 0.01 and above, it's small correlation. 0.01 and above, and less than 0.09, that's small correlation. And the medium correlation is 0.09 and above, and less than this, 0.25. And large correlation is anything over 0.25 and above. So in our example, it was a large correlation. So the interpretation is like, this is a large correlation. 40. Okay, so we get this number, 42%. So what is 42%? What is 42% is that the variability in one variable is explained by its relationship with the other variable. So this and this are related. 40% of all the sampling data. So in this case, there's 14 people, so it's probably like 6 people. 6 of them can be explained by the correlation here. Explain. It's not the best way to say. What should I say? One variable explained by its relationship. Anyway, this is a large correlation. The key is 42% of the variability in one variable is explained by its relationship with the other variable. 42%, 100% is probably definitely the largest, but 42% is kind of small, but still considered to be a large correlation.